Hi, I'm Tom and I talk about code. Welcome to another Rust programming live stream where today I'm going to be working on my compiler. I did a bunch of stuff off camera. This is mostly an off-camera project. Unfortunately, my plan was to do a lot of it on camera, but life happens. And my goal today is to do argument passing because I got locals working. I got my function calling working. I was kind of stuck in the middle of that last stream, but I've got a function calling convention. So when we call a function, oh my gosh, I can't write. When we call a function f, okay, there's a few things we have to do. I'm just gonna quickly outline what happens, right? Because I've got a couple of handwritten notes. So we have a function f, right? And let's say we pass three numbers to it, 1, 2, and 3. Okay. So the first thing we're gonna do is to push 3 onto the stack, then we're going to push 2 onto the stack, then we're going to push 1 onto the stack. We push the arguments onto the stack. This should hopefully make sense. When we want to call a function, we want to make sure we can use the arguments. Then, so this is like the argument part, then we do the stack frame setup. We push the current base pointer, we push the current program counter, then we set the base pointer to be equal to the current stack pointer. In other words, like what the stack points to at this point. And then we set the PC to the address of our function f. Okay, so this sets up two really important things. The first is, and then once we jump to f, the other thing we have to do is increment the stack pointer by 2 times the number of locals. Also very important. So then we end up with what I've kind of been calling a stack frame, right? So let's use a different color. Let's draw it out. We have this kind of block of memory that's going to look like this. It's going to be arg n minus 1 ... arg 0. Then we have the old base pointer, which I'm going to call base pointer prime. We have the old program counter, which I'm going to call program counter prime. Then we're going to have local 0, local 1, etc. That should be a 1. Cool. Okay, and the base pointer points here. So I've got the local wrangling working. That's all fine. Now when I want to access an argument in the function, right? So the function's running, we're in the body of f. Anytime we want to access an argument, well, we can just reach backwards from whatever the base pointer points to. And thankfully, the way I've set up my virtual machine, I actually have an instruction to load something from an offset of the stack. Well, this is the base pointer, this isn't our stack pointer. My instructions take a register as an argument, so you can use a different thing as a register. So basically we can say, from this stack, take the thing at an offset. I don't even think the word stack really needs to feature. What we're really saying is load the 16-bit word at an offset as if this is an array or something, except an array that grows towards like this way is higher indexes. It grows towards whatever the heap base is, and this way is towards 0. Okay, I think we're good. I think that makes sense. So in other words, actually no, that's backwards. Our stack grows up. This way is positive. Is this right? Maybe it shouldn't be like this. But that's okay. That's okay. This will do for now. I can't remember why I did it like this. Now that I'm saying it out loud, it seems a little silly. Either way, we have machinery. We have an instruction that's going to let us take this base pointer and load the 16-bit word at a negative offset from it. So in other words, if we want to get the program counter, we can get offset. I'm going to swap back to my original color here so it'll look a bit cleaner. We can ask for offset 0. If we want to get the base pointer, we can ask for offset 1, 2, ... n plus 1, and n plus 2. Yeah? So if we want argument, well, it's actually a little bit, if we want argument n, argument I, we look for 2 plus I, as long as I is less than n. Beautiful, beautiful. We can do this. The other thing is we need to actually push these onto the stack. Now, I started writing this earlier, and I can't quite remember where I got up to, so we're going to have to look at that. We're going to have to think. We're going to have to recall what's going on. I'm currently in the middle of some issues with the parser, because this is the other thing. When you write all this stuff yourself, you end up with these layers, right? So you're like, okay, I can do function calls. I can do function calls that, ignore the fact this is called sum, I should call it add instead. I can do function calls that don't have any parameters, that's fine. And then you try and add parameters, and then you run it, and it's like, hey, why is there a variable in here? Even though you've told it to parse. And I know why this is happening. I just, it's complicated. So all that stuff I just said, we're actually just going to park that for a second. We're just going to park that for a second, and we're going to dive into Parserland. Because this is what happens when you write your own programming language for your own virtual machine. You're juggling lots of stuff. There's lots of stuff going on. This is not working properly. I'm trying to, have this delimited list of named arguments, and there's a problem with it. And the problem with it is, this, I don't think this works. Yeah. So the problem with it here is, when there's no arguments, it expects there to be an argument. But when there is an argument, it's also not happy with that either, because A isn't defined. Okay, that's actually fine. That's just saying this. So if I change this to 1, then this will work. Cool. And for some reason, it's not compiling this next function and realizing there's an unknown variable. That's okay. We can do with that for now. So we build main. Cool. That's good. But this is a problem, right? And actually, if I make t, one of my tests will fail. So thankfully, one of my tests caught this. What test is this? Test function. This one that tests an empty function. Awesome. So how do we support parsing an empty function when we sometimes might expect there to be things inside of it? Function definition. Well, it's all going to come down to how we defined this delimited combinator. So we can jump into our parser combinator library that I've written. Again, a reason to not go this many layers deep. It gets very chaotic when some things break, but that's okay. Now, if we try to, if we run our parser and it fails, that's an error. But we don't want this to be an error. See, I wrote this function called at least 1, but I actually want the opposite. I want 0 to be valid. I want an error to just mean empty list. So let's just rewrite this function, because I did the inverse. Let's call it allow empty, okay? And it's going to take a thing that returns a vec_t. We're going to run it. We're going to match on the output of this. Match. And then, if it's okay, that's great. We just pass on whatever came out. If it's an error, then we're going to say, okay, if it's an error, we're going to say, okay, input vec new. Right? So either it's okay and we got something, or we got an error, but that's actually okay as well. We're just going to pretend everything's okay and pass along an empty list. So this is now called allow empty, which should resolve this problem nicely if I can put my closing parentheses in properly. Okay, now, this has a problem. This has a very important problem. Partly that there's a ghost parameter. I don't know how that got in there. It just kind of snuck its way in. You know, sometimes these parameters like to appear. Value used here after move. Okay, so this needs to be, well, I mean, first off, we can get rid of this, but one of our generic parameters needs to be clonable so that we can clone it, because closures are weird. I was telling someone at a Rust meetup the other day that my Rust IDE experience was just Vim quick fix lists and rebuilding often, and I didn't even have like red squiggly underlines or anything. They thought I was a bit crazy. Input has type S, which does not implement the copy trait. Sorry, I need to clone it here. And I think here as well, but let's find out. Okay, now what if I remove this? This is one of my favorite ways of playing with the borrow checker. Okay, perfect. And it looks like everything passed. So we fixed it. So now, beautiful. This test, well, this compiles. It successfully gets here and is like, hey, I don't know what the hell this thing X is. So let's give it an X. And now if I run this, it's still going to complain. It's going to complain because, and I printed this out to the console to make it easier to see, our function definition does not seem to understand that there are arguments. Okay, well, why would that be? Let's go back to our parser. Let's go back, if I can work out how to type, let's go back to our parser. What do we do when we get the list of arguments? Well, we just ignore it. We need to store this somewhere. And we need to move it on through. This should be okay. Identify a type. Okay, so we gotta map this through. We probably want to map it here, right? We want to make things easier. Identifier, we're gonna map the identifier and we're gonna map it from a string into an identifier. And actually, can I do this without the explicit closure? Can I make this implicit? Can I use this as a constructor? AST identifier. Haha, that's a trick. No, okay. AST identifier new X. Now this will work. Now this will work. Wait. Did I do that backwards? Did I misread my error? Expected identifier found args. Yeah. So a function definition, it wants. Wait. Args. AST type. String. Okay. args.iter.map. We have the ID and we have the type, and we want to map that to id.0.to string and the type. Okay, now we just have a good old-fashioned syntax error. Collect vec. Why am I... Oh, yep, that needs to be wrapped in angle braces. That makes sense. Cool. Unknown field. ID. Let's build before we test, because then this will be easier to read. Expected identifier found string. Function definition. Oh, because in the AST, I wasn't paying attention. It does actually want an identifier. So, why? Okay, so this is a string. We want an identifier. But I thought identifier returned an identifier, right? This returns an identifier. So why is it confused about what it wants here? I'm giving you what you want. Right? What does it say? Vec identifier type found vec string type, but we're getting back args allow empty delimited named arg. That makes sense. Okay, so let's stop being silly. Of course, it was exactly what I was telling it to do, because the computer's always right. You know, the computer always wins these disagreements. I don't know if you've noticed. It has a way of keeping track of what's going on that I don't. Okay, so now back to what I was drawing before. This took a little bit, right? But we're here. So we can parse functions that take arguments. But when we try and compile this, does it work now? No, it panics. But that's good. That's good. We can see that this function now has an argument that gets passed into it. That's really good news. And now we get this panic, and this is a panic that I put in. I put this here. Was it 281? No, that was not the function, the line at all. Compile mod 281. There was the right line, wrong file. Okay, so when we're dereferencing a variable for our compiler, we see if it's defined, and if it is defined, we check if it's a local. If it's a local, we have to do this nonsense. If it's an arg, it's going to be even better, right? Block variable arg. Okay, so we're going to get a couple of instructions in a vec. This is very inefficient, but that's okay. Okay, so it's an arg. And eventually we're going to do some smart stuff about working out like if we can put stuff in registers, but that is going to be iteratively bolted on top of this very dumb layer, this very dumb code gen. Maybe. Or maybe I'm going to regret not doing it up front, and then it'll be too hard and I just won't do it. We'll see where we end up. Okay, so arg. Now, like I was saying, right, we just get the offset of the word relative to the base pointer. So there's an instruction for this. And we're going to copy and paste because I don't like typing out this many letters. Unresolved instruction. The instruction is going to be load stack offset. And if we can look at how this is defined, load stack offset. We take a target, we take the target register that we'll be assigning to, we take the stack pointer register that we'll be using, and we take a word offset that is a nibble. So this is register, so let's use C. C is kind of C for clobber, the register that we just do whatever with. Relative to the base pointer, we're going to get a nibble, and new checked, and it's going to be I plus 2, right? Because arg0 is at position 2, etc., etc., etc. Beautiful. And we're going to unwrap this because I can't think of how we will possibly deal with this uncertainty right now. I don't know how we're going to deal with that error. We're going to have to be smarter. We're going to have to we're going to have to do some logic before we just return a big dumb list of instructions to make sure you don't have a fallback. Like if there are too many arguments, we just don't do this. So what happens if I compile now? Try into. Yep, that makes sense. So we need to go I as U8 plus 2. Okay, cool. So we print some garbage out, and that's pretty good. That's quite good, in fact. Now there is something missing here as well, and that is pushing this to the stack. We don't just dump it into a register. We always push all of our expressions when we're done with them onto the stack. This makes the compiler really simple. It makes it really, really easy to write a compiler in 400 lines of code. Like this is the whole compiler, right? Apart from this is all the code generation rather of the compiler. All the parsing, you know, that's complicated in a different way. But this is it. This is how we do code gen, and it's this simple. I mean, simple, right? It's a freaking nightmare. It's a horrible 400-line file that I wouldn't wish my worst enemy to read, but it's pretty simple because we don't have to think about registers and what's in registers at any given time. We can just dump everything onto the stack. So let's get rid of our gross println debugging. Is there anything else here? Yeah, there's another one. Define arg. Cool. Excellent. Okay, so now let's pipe this through to our disassembler. Excellent. Okay, that looks good. I didn't read it, but it looks good. So let's see if we can calculate 5 plus 1. Wouldn't that be cool? Wouldn't that be really cool? And it compiles into something. Let's copy it and let's bring it off into temper theta delta EU stream. Yeah, what time is it in Europe right now? I have no idea. All I know about time in Europe is that I might be commentating a Quake tournament at like 8 a.m. Next Sunday, which is late at night on Saturday in Europe. Man, 1:30? Yeah, wow. So it's like 9:30 p.m. here. That's quite different. Which, you know, we all know, but it's always surprising somehow. Okay, so actually let me use a different web browser for this. Okay, I've got my VM up. I didn't make sure I didn't have anything like weird up in the background before I started streaming, which is always a bit of a risk, right? But that's okay. That's okay. My God, it's very bright. It's a very white page, and I feel like I'm like being blown away by it. That's not right. Okay, and then it blew up and cried at me. Failed to print STD out. That's what I wanted. Okay, so what happens if I run this? We get something. We get something. Let me zoom in. Hold on. That's probably a little nicer, right? So what I would expect here, because functions return in the A register. Functions always use the A register to return their return value. So what I would expect to see here would be the number 6, okay? What do we get in the A register? So this is only, right? This is only 267. No, that's not right. That's two. Whatever that number is, it's only 16,000 wrong. So what I think has probably happened here is that we've somehow added 1 to the old base pointer, maybe the old stack pointer, something that we should not have added 1 to. So it appears, because we're never gonna, like this is 1 more than what's in the B register right now, right? And what looks interesting about this to me is that it's an odd number. And because this is a 16-bit VM, all of our reads and writes, we usually read and write 16 bits at a time from even boundaries. If we try and write from an odd boundary or read from an odd boundary, we blow up. That's not okay, right? We are 16-bit word aligned. The fact that this is off by 1 tells me that this is the thing we've added 1 to. Okay, so what we're going to do, we're going to reset the machine, we're going to compile, and we're going to step through this bit by bit. So we shift left, we push, we jump at this point into the main function. Now what do we do in the main function? Well, we create a variable foo, which should be the first local. So, and again, we can refer back to, if I can find it. So foo, so if our base pointer, right, at this point, which is 16372, so let's make a note of this, right? Let's annotate this as if we're really calculating it. Because we are 16372. Okay, so our first local is at this address, at whatever's in the base pointer. Is it? Or is... Yeah, it is. So this is actually 1, and then this is 2, then this is 3. I think I see what's happened here. Because if we read base pointer plus 2, which is what I told it that arg0 was, we would get the base pointer, which would explain why we had, if I run this through to the end, this strange number in the A register. I'm trying to highlight this. For some reason, I can't highlight any of this text, but I'm looking over here. It'll follow the menu. Jerogoras, that's not a real person. Let me get rid of him. Let me get rid of this guy. I got excited for a second there. I was like, hey, okay, I think they're gone. I just swapped into like streamer mode. I saw a name and I shouted it out. Okay, let's go compile. And where we block variable arg, we just come in here, and where it's +2, we're going to change it into a +3. We're going to recompile our code. We're going to paste it in here. We're going to reset. We're going to compile. We're going to run. And like, that's better. That's more like a real answer. Okay? Vaguely. That's vaguely more like a real answer. So that's good. That's good news. Let me just convince myself that I can actually do math at all. So let's maybe say 1 plus 2, right? And we should see 3 in reset, compile, run, 3 in the A register. So that's good. Oh, do you know what? Do you know what I don't do? After I call a function... I mean, that doesn't matter. After you call a function, after you return, so like you've got all this shit on the stack, right? And then when you return from a function, the first thing that happens are the vague steps. The vague steps are, let me swap over to my proper drawing scene for this. The vague steps are, we get one of the things we do is we say stack pointer is base pointer minus 4, I think, right? And then that sets the new stack pointer to be back here, which is where it was before we started pushing all of this frame nonsense onto the stack. The problem is we're left with a bunch of args on the stack, but because stacks like grow, like our stack grows this way, it doesn't actually matter if we accumulate garbage here. So we don't need to worry about doing, you know, like this next operation of stack pointer. Like this is in the called function, and then in the callee on return we have to do stack pointer equals stack pointer minus 2 times the number of args that we just pushed. But the cooler, let's call it cooler. I think my terminology was bad there. The cooler knows how many args it passed, so it can always work out how much to shift the stack. I don't think that's something the called function should concern itself with. Maybe. I don't know. That's a little opinionated. Let's just put a little marker here, after. Okay, so. I'm back to stepping through the function to work out what's going on. So let's change this back to calculating foo. Let's copy it. And let's go in. We're going to reset, we're going to compile, and we're going to step through this bit by bit, shift, blah, 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 jump into main. Now, what does main do? Okay, so we're going to push 5, so that's good. BPSP push, add SP0P. So now that we've pushed this, we set up and we jump to PC62, which is going to be our add function. What's the first thing we do? Add in SP0. Now this is the thing that should allocate room for locals. We probably need a check that says if there are no locals, just skip this. Because this is a bit silly, but that's okay. So we add 0 to the stack pointer. This is a no-op. We load C, we push C. Now, we load the offset into C, which is the number 5. That's, oh, whoa. I'm stepping through blind. You're just like trusting. This is like VM, like the audiobook, the podcast version of this show. Okay, the conclusion is we've got 5 in the C register, which is what we want to see. We've put it in our clobber register. And I think the next thing we're going to do is push it onto the stack, which, yeah, so we push it onto the stack. Then we add the top of the stack, and then we pop the top of the stack into A, and we get 6. So that is the correct answer. Because we have like this generic set of stack operations, and one of them is to add the top 2 things of the stack, which is a cool way to deal with this kind of chained expression. And I think it would mean a smarter person could do some really cool stuff writing a compiler for this system. Not me, but, you know, I mean, that was kind of clean, right? So the A register has our return value in it. Then we do some stuff. We load the program counter, then we jump back to this point where we push A to the stack. Now that's, where's that? 5, that's here. We're back here, okay? So we push A to the stack, then we pop C off the stack, and we're going to store it in a local. Now this is where things get dicey. We're going to store it in a local. So we get b. B is our base pointer. Then we add 0 to it because our first local is just at the base pointer. That's where we write it to. So we store c at this place. Now we're going to set up to... Not sure what we did then. Add BP... C gets the value of the base pointer. Stack C, PC, push. Load C, C0. I'm not sure what I did then. I'm not sure what that is. What's this instruction? Why do we dereference here? Store B. So this just stores the local, which is fine. Add BP. So we set C to the base pointer. So this is local 0. We just read local 0. And then we push it to the stack, and then we pop it off the stack. Okay, so what we do here, what we do in this sequence of instructions, this is the stupidest compiler ever. It knows that it needs to get the thing we want to return into the A register. It doesn't know that we already have it in the C register. And it also doesn't... All it knows is there's a local called foo that we have at some point stored a value to. It is ignorant to the fact that value is in both the C and the A registers right now. Not just one register, it is in 2 registers. Despite this, we are going to take the long way around. We're going to load the base pointer into C, because this is how we dereference locals. We then increment the base pointer to the correct place. In this case, again, performing a no-op because the first local 0 is just at the base pointer. We then dereference C into itself. So this is where we load the value into register C. So actually, we only had it in 1 register. That's... Oh no, we had it in 2 registers. We've just done a bunch of work to load the same number into C. That's great. Now we're going to push it to the stack. Then we pop it from the stack into A, but this also doesn't do anything because A already was the value 6. Again, this is like a no-op, but that's okay. Now we're going to set ourselves up to return. Okay, we're setting it all up. We've got our new program counter. We're about to, yep, we jump to it. Now we load and we loop back around. That's not right. Wait. Well, that's weird. Yeah, this is all kinds of whacked out. C, BP, load stack offset, C, BP, 0. Okay, so what happened there was very weird. Was I think we almost got to the end. Oops, reset, compile. We got to the end, but we didn't end. So let's just watch this PC. Store. Now we do this very silly thing where we go from having 6 in register C to having the address of the local that has the value of 6 in register C to then having, again, the value 6 in register C. Oh my god. Now we're getting ready to return. We're doing returny things. Add immediate. So we're jumping back to address 12, C. Now we jump back here. We jump back here, and this is right. So then why is this not... Well, this is the end, right? This is it. We just hit a halt instruction. If I hit step again, we're going to keep stepping, but that's only because I'm an idiot. So if I run this, we get 6 in the A register, which I swear is not what we had before. Let's try a different number. Let's try 12. That's a bigger number, right? It's a much more impressive, larger magnitude number. Reset, compile, run, 13 in the A register. Okay. In conclusion, that worked the whole time I was talking. I did all that for nothing. You know when you're like following one of those traces through and you're like, you feel yourself going crazy because you're like, this works. Why didn't it work? Why did I get the wrong answer? And you realize that it actually did get the right answer. You either looked at a test from an old like binary or an old test case, or you looked at the wrong thing and you just wasted your own time. Beautiful. Okay, so we can do arguments. Can we do more arguments? Can we do 2 arguments? Is this ambitious? Is this a little bit scary, perhaps? Okay, now we're getting into the meat and potatoes. Why can't we do this? Expected semicolon got open bracket. Oh, you know what? I feel like function calls aren't done correctly, right? Because function definitions, sure, we've got this delimited thing. What about call? Expression call. Yeah, so we just repeat the expression, but what we actually want is allow empty delimited expression token. Yes, so this. Okay. That didn't change anything. Make t. I didn't break any of my tests. So let's make a test that should hopefully fail. Test expression, cool. This is a bit stupid, but I've just been doing these tests like this where I do multiple tests in one function and I wrap them in a block so that they have their own scopes. Foo, 1, 2, 3. Okay, make t. And this is gonna blow up on me because we expected close bracket and we got 1. Now, why is this? Why is this? Expression call. Expression call. Let's put a marker here and let's jump up to expression call. Okay, so. And delimited. Let's get rid of the skip white space. Actually, maybe we should add a skip white space. That's probably the problem, right? The skip white space. So if I do this, maybe it works. Yeah. So the problem is literally the white space. And we can deal with that. We can go here and we can say skip white space, because we have to skip the white space within the thing we're delimiting. We don't want to skip white space then look for the delimiter, because it doesn't matter if there's a space after it. I'll demonstrate this in a second. That now works. Beautiful. Like, it shouldn't matter if this is our case or if this is our case, right? This is going to fail the test because the string's wrong, but it still parses. Okay, so now we can do this, and I can paste this, reset, compile, run, and we get 14 in A. So that's pretty good. That's pretty good. That means this works. That means we have function calls. So now that we have function calls, can we do fun stuff? I guess not quite. So let's git add source bin lang. Nice. That's really good. That's really good. So we have this test file, right? What I would really love is to be able to do Fibonacci numbers, or even just like a recursive sum. So I could maybe say int sum, and this is where this came from, or int. What are these called? Where you, yeah, I guess ord, nth. Like 1 plus, oh, let's do fact. Let's do a factorial. I'm gonna have to do multiplication. Actually, no, I don't have soft multiplication, so let's just do it as if we're adding. So we'll say if, no, we don't have an if statement yet. We're gonna have to parse this. If I is greater than 0, then we're gonna say return I plus 1, else, no we're not, we're gonna say return nth I plus 1. Is that what I want to do? Is this what I want to do? What am I doing? I'm counting, right? So if it's 3, we'll go 3, 2, 1. This is much better with multiplication. This is so much better with multiplication. I mean, maybe fib is better. Okay, I need to Google it though. Fib numbers. I can never remember the exact formula. I should, right? It's just, yeah. F of 0 is 0, f of 1 is 1, f of n is, yeah, it's just the sum of the previous two. Okay, let's do fib. Let's do fib I. If I equals 0. Oh god, this is actually going to be more complicated than I thought. Am I ready to tackle if statements right now? We should. We should do it. So if I equals 0, then it's return 0, else elif I equals 1, return 1, else return fib I minus 1 plus fib I minus 2. Yeah. Actually, we can make this simpler. We can, because else if is hard. We can say if I is less than or equal to 1, we return I. This way, we kind of skirt the awkward. Well, it just is. We don't have to worry about else if, because that stresses me out. Honestly, it's almost 10 p.m. Thinking about that. That's not what I want to be thinking about before I go to bed. I don't want to have nightmares tonight. So let's try and fib it up. Let's try and work out the 5th Fibonacci number. Now, if I try and compile this right now, of course we're going to get an error. And that error is going to say unknown symbol fib. And it's going to say that because for some reason if we fail to parse a function, it just doesn't get defined. So that's great. That's really cool. That makes me happy. First things first, we need to define the actual structures. So in our list of statements, let's define an if statement, which is going to take, it's going to take an expression. Actually, let's make this a named one because we're going to have a condition, which is an expression. We're going to have now, we're going to have a body, which is going to be a list of statements, and we're going to have else body, which is going to be an option vec statement. Okay, that's a bit ambitious in a sense. I think that's okay. And because we don't really have like a block type, do we? Yeah, bodies are just lists of statements. Now, this could just contain another if, right? So you could kind of get if else by just chaining these together. And I think that's kind of how Rust does it internally, right? Because they're all expressions anyway, so it's a little different. Okay, so display statement self if. We'll do if cond body else body. Can I do a guard here? Maybe not. Maybe it's easier to just accept my fate. If let sum equals else body, then we're gonna write to the writer if cond body. I guess we'll just put a thing here, and then we'll have an else with a line and an else body. Okay, good hustle, everyone. That was good. That felt like we were onto something there. Else, we're just gonna do the same thing without the else body. Okay, beautiful. Now we just need this awkward monstrosity, which is gonna be body.iter. Map lambda x.to string. So we get a string representation of every statement in the if statement body, then we collect it, then we join it together with a semicolon, I think. Join. I do this somewhere else. Not in a different file. Join. Yeah, that's good. That's good to know. Okay, and then we just go E, the else body. We do the same thing. Here, we have it easier because there's only one body. It's beautiful. Cool. Except that doesn't get a comma at the end of it because this isn't inside a match. Okay, even though it feels like it's kind of inside a match, we're not inside a match. That was done correctly. Okay, so if I build now, it's gonna yell at me. It's gonna yell at me for a few reasons. The first is I continue to forget that I can't use these characters in format strings. So I just stick extra curly braces all around the place. Even though they're literally wrapped around, like, it could not be more obvious that that's not an appropriate place for a curly brace, but that's okay. Compile. Okay, so we need to support it when we compile. AST statement if. It has a body, it has a cond, it has a body, else body. Okay, now this is going to be complicated. This is going to be somewhat more complicated than anything we have done so far. Oh boy, oh boy. First off, let's assume we always have an else body. I think that makes sense. I think that's a reasonable and fair thing to assume. Okay, so. If C stuff else other stuff, okay? So the first thing is compiling this expression into something we can evaluate. Now, I think expressions, well, I'm going to go with the C world here, where, and it's funnily enough, I've called this condition C. So evaluate, I somehow selected the background color as my color, I think there. That was weird. Evaluate condition to top of stack, because everything always goes on top of the stack here. Then we pop, then we test if, let's say pop to C, confusingly, let's pop it to the B register just for now. Or let's call it R for register. Test if R is 1, right? If it's truthy. Or maybe even better, test if R is 0, test if it's not truthy. Because 0 is falsy and everything else is truthy. I think that's a sensible way to think about it. Okay, so if R is 0, then we need to, if this condition is false, then we jump. If R is 0, then jump to label. Otherwise, stuff here, right? And this is a good way to do it, because this is the same regardless of whether we let's actually call this label 0. This is the same regardless of whether we have an else body or not. If there's an else body, then this goes here, but if not, then we just jump to LBL, let's call it label X. Okay, then we have label O and the truthy part of the function, and then we have a label X, which is our jumping out point. So let me draw it in a different color so it's a bit clearer. This corresponds to this. This is the same part of our code. Okay, so one thing you're going to notice is we use these labels, but where do these labels come from? We don't want to have to think about this, right? We just don't want to be thinking about what these offsets are. We don't want to have to calculate all this and then work it out. So one part of the reason that this code is so disgusting to write is that I have this unresolved instruction stuff everywhere. And the cool thing about unresolved instruction is that it lets us define an instruction that takes a symbol. So instead of jumping, I guess this is like setting the program counter to something specifically rather than just jumping to an offset. But, we'll use this instruction, but we don't need to give it the actual address we're jumping to. We just give it a symbol. And that symbol is resolved in the last pass of the compiler once all other symbols are known. We can also insert a label, which is an instruction that takes up no space in the final program, but instructs the compiler to remember this spot in the program as a destination that we can jump to. Does that make sense? I hope it makes sense. Because we're about to do it. We're about to find out the hard way if this is enough to build something off of. Okay, so where are we? If. What do I have to do? We evaluate the conditions. So we're going to say, we're going to make vec new. Actually, no, we're not, because we're just pushing these straight into the block. So we're gonna get a mutable copy of the compiled condition, which is just a compiled expression that takes a block and the condition that we're passing in. Okay, so we've compiled the condition. This will push something onto the stack. That thing that gets pushed onto the stack, we want to pop off and test for truthiness. So first off, let's block.instructions.append. We're going to append the compiled condition. Okay, test if condition is falsy. So we're going to push an instruction. The instruction is going to be instruction, too many instances of the word instruction. Instruction pop stack. We're going to pop from the stack into register C. Excellent. We're going to pop off the stack into register C. Then we're going to test. Okay, so we're going to test both 0, which is a really cool little hack for me. So we're going to use this test instruction. We're going to say test. We're going to test register C. We're going to test if register C and register 0 are both 0. Okay, so this is our test instruction, the one that does truthy stuff. If register C and register 0 are both 0, then this will be true. If this is true, then we'll jump. And our conditional jump instruction is our add if. Now add if is relative. Add if is relative. Do I need a set if? Do I need an im if? Maybe I need a new instruction here. Add if. Can I do this? Can I do this? Can I do this with offsets? It makes more sense in a way, right? I've got this jump offset. Maybe offset. Maybe when I resolve in an offset instruction a symbol, I should do like the distance to that symbol. Right? No? It's almost like I need both. Okay, well, let's park that for now because we can actually compile the next bit. Let's put it here. Let's say add if. Well, I guess I can just step over a couple of instructions as well. So, block instructions. So it's add if register PC, and it's going to be literal 7-bit, I guess, if it's just one thing. New checked I. We'll just call it I for now. Okay, so this is okay. This is okay. No one panic. Nobody panic. We're just gonna make this bit. So if this is true, then so if this is 0, then we skip over. So now, so this is like backwards, right? So what we're saying, if this is 0, then we do add to the program counter, which means we're gonna skip the next instruction, which is gonna be a something that sets the immediate. It's gonna set the program counter to symbol new okay. Yeah, so this is good. This is good. We can just use addif to do little steps, but we can step over the big jumps. I feel like this is devolving into nonsense. This is so complicated, and there are so many moving parts, and I have streamed so little of this. Okay, so if this is falsy, then we're gonna step over the next instruction. So we're just gonna add 4, 2. I think we just add 2. No, we add 4. We add 4. Because this is PC plus 2. We're going to go to PC plus 4. I'm pretty sure. So we jump over an instruction. This takes us... This is executed if it is false. So this is to the false. Let's call it label false. We are now in condition equals true. So we need to compile the body and insert this. That was a very long way to get here. Now, I actually haven't done this recursive bit before, and I kind of need to split this into 2 functions. So let's see if we can do that real quick without blowing everything up. This continues to just be the... now, where is offset used? That's fine. Okay, so yeah, so this is good, right? So the actual block, the overall function needs to know where it exists, but this inner block does not need to know the function name or where it is, I don't think. But we're going to return a block. We're going to return... No, we're going to return a vec of unresolved instructions or a compiler error. Okay, this is what we want. This is what we want. This is where we have the... Actually, this should take a block as well, shouldn't it? This is going to take a block as well. It's going to take a block. Okay, so this is where we do this. This is where we do this. Local... And that's just at the end. Yeah, okay, cool. So for this bit, this part of the block lives in its own function, and we can call this specific part recursively. Cool. This is good. This is good. Let's say out equals vec new. Now everywhere we say block.instructions, we want to replace this with out. Just in this bit, we're going to say block.instructions. We're going to replace it with out. Wonderful. Wonderful, wonderful, wonderful. Okay, so we come in here. In between load return address. Yeah, so after, so this is a Then we're going to say block.instructions.append mut compile block. We're going to take the context, we're going to take a mutable reference to the block, we're going to take the statements, and we're going to unerror that. Okay, that looks good. That looks good. I think. I think we're good. I think we're good. Okay, so now we say out.append. We do the same thing again, right? We do it recursively. We say out.append compile block context block, and the statements are the body of the if statement. Now, have we borrowed anything from block? No, we're okay. We can pass these through. I think this shouldn't be a borrow checker violation. I'm a little bit nervous. I'm a teeny bit nervous that we might have a borrow checker violation, but I think we're okay. Okay, so now we're gonna, now we've done this, we also then have to out push, we have to jump to this one. We have to do this, label out. Okay. And this is where we need like a gensim function that just makes up a random label that identifies this block. But for now, I probably want to do something stupider because we only have one if statement. I might just make it the same thing every time, right? So I might just say let label false equals symbol new, and we'll just say label false, and label exit is going to be label exit. Label out. Let's go with label out, maybe. I don't know. It doesn't matter what we call it. No one's ever going to see this. This is machine internal. Okay, so when the condition's true, we do the true stuff, then we jump to the out. Condition is false. If let some body, if the else body is not none, then we want to do this, but for the else body. And then after this, after we've compiled the else body, then we're done. We don't have to do anything else. We don't have to do any more jumps. So we just go straight to, oh, hold on. If this is it, we need the label as well. So this is where we put a label. Label. And then we also put in a label for jumping out. So this could duplicate labels, right? But it doesn't really matter. They'll compile down to the same thing anyway. Okay, this feels like code. This feels real. This feels like something we can do. What happens if I build this? It yells, it screams at me. First things first, I haven't included test op. So that's nice. Label out, local variable, label exit. Label, no, I'm just gonna call it label out everywhere. I don't know why I've made this harder than it needs to be. Label out. Okay, what's going on here? Instructions. Except I don't want that. I want out.append. Yeah, excellent. Okay, instruction add if. Register found literal 7-bit. That's interesting. Oh yeah, that's right. No, it's nibble. Register 0. I have an extra offset there I forgot about, I'm pretty sure. Okay, so add append expected mut. Yep, that also checks out. I just forgot to unwrap my errors. Excellent. This is fewer errors than I thought. So you don't need an IDE. You don't need that. Uh-oh, we got a problem. We got a borrow checker. We got a live one. compile block implicitly returns nothing. That's because we need to come down here and we need to say out. Okay, well that's gonna fix that, but we still got, we just need to say okay, out. We still got this borrow checker. Okay. So this is annoying, right? Because we want to be able to say, wait, hold on. Where's the borrow checker issue? Block not mutable. Compile expressions 184. Hold on. Whoa. 184. Yeah, because we don't need, this block is now already a mutable reference. That's fine. Block not mutable. Use of, oh, we need to clone it the first time it's used. And then it gets moved. Okay, cn. So this block instructions. Okay, so let mut compiled. This is really annoying because we want to mutably borrow this when we call this, but Rust can't assert that this is okay if we call this, if this is all wrapped up like this. So we need to just split it out into its own little bit. If that makes sense. Hopefully that makes sense. The borrow checker will be happy now. We have appeased the borrow checker gods. Block not mutable. What is going on here? Cannot borrow block as mutable as it's not declared as mutable. Where are we borrowing it as mutable? 213. Oh shit, it's bin night. I haven't taken my bin out. Damn it. Why does this happen every bin night? It's 10:30. It's going to be late. It's going to be dark and scary. Schrodinger's borrow checker. Exactly. You never know what you've borrowed until it's too late. Okay. So inside this function now, every time we mutably borrow block, it's no longer a mutable borrow. We've already mutably borrowed it. We can just pass it on through. Nice. Okay. I didn't expect that to work. What happens if I build? It still doesn't work. Now, though the eagle-eyed viewer may realize why this didn't work, okay? the eagle-eyed viewer may have noticed that I forgot to do something very important. And that something is actually parse it. Let's see how good my parser combinators are. Let's see how quickly I can do this. Let's go statement if. Okay, so we're going to give back AST statement. That is okay. I need to do better error handling here at some point. The more time I leave it, the more it's going to hurt. But I just can't right now. Maybe I should do this as a sequence, because it's going to be long. Nah, screw it. I'm just going to keep doing this weird thing. Skip white space token if. Very important way to start, okay? If. First thing in that if statement. Then we're going to have well, it's actually going to be a delimited, right? So we're going to have let s1 cond equal a wrapped, sorry. It's going to be wrapped. It's going to be a skip white space token open parentheses. Then we're going to have an expression. Then we're going to have a skip white space token closed parentheses. Oh baby. Now you're talking my language. Okay, so this is our condition. Then we're gonna have a skip white space open bracket. Except it's gonna be a token open bracket. Then we're gonna have at the end a skip white space token closed bracket. But how on earth do we get here? How do we get between these two states? What comes in the middle? What comes in the middle is the body. And all the body is a delimited list of statements. So let S3 body. So we're going to skip. We're not going to skip white space here. We're going to say allow empty delimited statement, and they're going to be delimited by a skip white space token of a half a winky face. Okay, does that feel good? Does that seem right? Isn't it just a block? Do I already have a block? How did I do function? This is a good point. This is a good point, Temper Theta Delta. I'm already parsing a block. How do I do... Where's function definition? Yeah, okay. So I'm doing it as a special. It's a snowflake. This one's actually going to be better because I'm going to use delimited, which is better than what I was doing before. Cool. That's okay. And this, I think, actually also should be a skip white space. So in conclusion, I'm kind of already doing a block, but I'm not doing it as well as I could. So I'm going to do this, and then this is going to become the definitive block. This is going to be it. Let's try this first. I feel like because if is the most complicated pattern, I should put it here. I should try and do it first. Okay, that actually just doesn't build. That's good. S3. 1, 2, 3, and then we say okay. SN cond body else body none. We're just going to do this for now and see if it builds. That's close. Try wrapping the pattern in because we forgot a question mark twice. Excellent. What if I build this? Unknown symbol fib, that's annoyingly all I get. So if I delete the else case, how does this look? Still nothing. Nothing. If I get rid of main, expected closing bracket got I. Closing bracket got I. This is likely closing bracket got I. Okay, well this is apparently still an issue with the... There we go. Expected return got if I. So it's struggling to parse it. Oh god, okay. We're making progress, but I'm probably going to have to call it there. I need to write better errors for my parser combinators. So I'm going to let myself get distracted and do that, maybe off camera, so I can come back and actually troubleshoot this in a sensible way. Otherwise, this is going to be a nightmare. I got a couple of viewers. Let's find someone fun to raid, and then I'll go take my bins out. Let me look at who's online. Software, game development. I'm always happy to take recommendations for cool people to raid if anyone has any suggestions. Hopefully someone on the smaller side who'll appreciate the 5 viewers. C++ game dev. These people will have like 100 viewers. They don't need my 5. They don't need my pity raid. Who are we gonna throw these people over to? ASMR programming, no talking. That looks solid. That looks like a really cool keyboard, which is always a plus. Who is a good person? Learning game dev with Godot is great. I want something weird. I want something kind of niche. Something kind of fun and niche. Bug fixing, great fox spirit. A lot of gamey stuff today. A lot of gamey things. Tower defense, wind in the trees. There's me. We're down in the dregs now. What have we got? Colt Zero, hello. I'm just finishing up and getting ready to raid someone. Who's a fun channel to raid to send people over to? And there's another Rust boy. Do I just throw it onto the other Rust stream? Who's this? Kuvi Man. I'm gonna have a quick look. I'm gonna vet him. I'm gonna do my 5-second. Oh god, I've got to watch an ad. I'm just gonna throw it over to this person. Here we go. Kuvi Man. I hope this guy's cool. Wonderful. Let's do it. Just throwing a couple of viewers over this way. But yeah, thanks for watching. It's been good fun. And yeah, hopefully back doing more soon. Hopefully with a more sensible error handling strategy. Oh, man. Errors. It's hard to do. Alright, I'm rambling. Have a good one. I'm gonna hit raid. Gonna do it. Here we go. Bye.